Hello, so welcome to this video. So if you're new to this channel, we mainly cover physics and talk a bit about maths and its application to physics, but so many times physicists are talking about imaginary numbers. Even engineers are using imaginary numbers, and one might wonder why on earth bother with numbers we call imaginary. And this video will be about exploring the physics of imaginary numbers. So really why physicists care about them so much. We'll be venturing from talking about linking distinct or seemingly distinct phenomena like a metronome and the growth of bacteria, all the way to quantum mechanics and talking about the necessity of using them in the context of matter waves and Schrodinger's equation. So we're going to cover a lot in this video. But don't worry, I won't be assuming any previous experience with imaginary numbers, because this is a video about explaining the importance of them in physics. This is not a pure maths video. So the focus of this will be why do physicists bother with imaginary numbers, particularly because if we think about physical quantities, there seems to be a massive mystery around why we bother with imaginary numbers. Because, if we're measuring any physical quantity, for example, the amount of coffee in a mug, the volume of water in a swimming pool, the light intensity from the sun, or even if we're using rules to determine values for physical quantities like the mass of the moon or the mass of the Milky Way galaxy, then all the numbers we get are real numbers. So why bother with imaginary numbers if the value for all physical observables are real numbers? Why bother with imaginary numbers at all? And if you're new to imaginary numbers, it's worth saying that imaginary numbers, despite not being something we can visually see, play a huge role in the hidden physics churning away in the universe. And as an introduction to imaginary numbers, we get imaginary numbers when we try to do the seemingly absurd thing of taking the square root of a negative number. Now, from high school, you might be thinking, well, knowledge of high school and maths, you might think, well, we can't do that. Well, we can't do that if we want to get a real number. There is no real number which is equal to the square root of a negative number. So if we're going to talk about square roots of negative numbers, we have to talk about a whole new class of numbers, and we call these imaginary numbers. And the starting point of imaginary numbers is I, which is defined to be the square root of -1. And it's a starting point because, as I leave as an exercise to anyone watching this who wants to have a bit of play with maths, you can express any imaginary number as a real number multiplied by I, where the real number will depend on what imaginary number you're trying to describe. So from I, we can construct all imaginary numbers, or all square roots of negative numbers, and then we can consider numbers which are combinations of real numbers and imaginary numbers. And when we have numbers which are combinations of these things, we call them complex numbers. Now, in truth, they're not too complicated, but complex numbers play a huge role in physics, and complex numbers contain imaginary numbers. They also contain all the real numbers. And we have a diagram on the screen showing how the complex numbers, in a sense, contain all the other numbers. And for most purposes in physics, complex numbers are all we need, but we do need complex numbers and we do need imaginary numbers, and this video is about why physicists care about them so much, and showing we haven't, completely gone mad. Not yet, at least. Not whilst, at least, kind of like we haven't disintegrated into, spending all our time worrying about string theory and higher dimensional space that we cannot yet possibly experimentally test. But that's an aside. For now, let's move on and talk about the massive importance of complex numbers in physics. So we're going to start this video by talking generically about extending the real numbers to include the imaginary numbers and build into the complex plane. And we're going to do this by justifying the need for imaginary numbers by considering an important part of particle physics, an important topic called spin, which is a property that fundamental particles possess. Also in this video, later on, we'll talk about the need for imaginary numbers, even when we're describing very classical things, such as, having maths that unifies things like waves on a string and the growth of bacteria. So, imaginary numbers are used in a huge number of places. But to start with, we're going to be talking about spin and using spin to justify extending the real numbers to the imaginary numbers. And if you can see a towel in this video, it's because Arwen, a very enthusiastic and feline learner of quantum mechanics, has decided to join me in this discussion and make an appearance for the channel, it seems. Now, Arwen is very talented at quantum mechanics, although I have yet to decipher her profound insights because they're mainly communicated through meows. But anyway, now with my fellow quantum theory physicist beside me, that's a venture into the realm of particle physics. So, the reason why, in the context, we need imaginary numbers if we're considering spin is based around the fact that there's a real restriction with the real numbers. So we think of real numbers as essentially sitting somewhere on a real number line. Now we're all familiar with the real number line, which we have a segment of in purple on the bottom of the screen, from all the way back in primary school. When we learn about adding and subtracting, we think about moving along this real number line. And the real number line contains positive numbers, it contains negative numbers, and it also contains zero. There's lots of fascinating things about this real number line, such as irrational numbers, which puzzled the mathematicians for a long time. But anyway, we have this real number line. But we can ask, and I'll explain why it's a but in a moment, but we can ask, how many numbers are 1 unit away from the number 0? In other words, if I move one step in the real number line, how many distinct numbers can I get to? Well, if I take one step to the right, I get the number 1. And if I take one step to the left, I get the number -1. So, if we want a number that's say A, and we claim that A is going to have to be a real number, that is, it's going to have to sit somewhere along this real number line, then the only values of A which are 1 unit away from 0 are 1 or -1. So, yeah, those are our two only options for A. And this is slightly too restrictive, and it's slightly too restrictive because our universe contains multiple spatial dimensions, and that means that we actually need more than just two numbers which are 1 unit away from the number 0. So what if we need more than 2 numbers which are 1 unit away from 0, or in other words, have a size, if you like to think of it like that, of 1? Mathematicians would say how many numbers have a modulus of 1, and what if we want to extend those numbers, the number of distinct numbers with a modulus equal to 1 beyond 2. That's using mathematical jargon, because mathematicians never like to be straightforward, so whereas most of us would say size, mathematicians say modulus for some rather unknown reason, apart from to confuse people, possibly, and make physics and maths sound far more confusing than it actually needs to be. And that was a slight, joke. So there is a good justification for having highly technical terms, but for our purpose, we just really want numbers which have a size of 1, and we want more than just 2 numbers to pick from. And an example of where we need more than 2 numbers is if we're considering spin. Now, spin is fundamentally a quantum mechanical relativistic effect. Even if you go to quantum mechanics and you ignore relativity, you're still forced to have this mysterious property of particles called spin that isn't really explained. It's only really when you unify quantum mechanics with special relativity, such as Dirac did in his Dirac equation, where you start to get a notion for what spin actually is. But for our purpose, and this is very much a classical analogy worth warning, we can think of spin as measuring how quickly particles are rotating about their own axis. So how fast, in less technical jargon, the particle is spinning. And it turns out that many particles, in fact all particles made up of matter particles, the matter particles, fundamental matter particles, have to carry some spin. And that often means things like, protons and neutrons, which are made up of these fundamental particles, will also possess spin. So many particles are, if you like, spinning, or at least the particles they're made from are spinning, including fundamental matter particles like electrons. So we can think of an electron spinning, and because an electron has charge, its spinning is kind of like moving charge. And if you know a bit about electromagnetism, you'll know moving charge creates a magnetic field. And therefore spin is important because it means fundamental particles like electrons, which are charged, actually generate a magnetic field. Also, non-fundamental particles, which also possess spin, like protons, also generate a magnetic field. The neutron is slightly subtle because although it's electrically neutral, its constituents, the quarks it's made up of, are not. And so we can still kind of talk about a field around the neutron in a manner of speaking. But let's stick with electrons. So electrons are charged particles. They spin and they kind of therefore act like tiny magnets. And that's why spin is important, because it tells us about this magnetic field produced. Well, we determine the direction the particle is rotating by having an arrow which has the direction of spin, and the direction of this arrow is associated with the direction the electron is rotating. And the direction it's rotating will indicate the magnetic field. So if you know what direction you're seeing spin goes in, you can tell about the direction of the magnetic field. So if we've got an electron, then this electron is free to move about three-dimensional space. So there is like three axes this spin arrow, if you like, can point along. It can point along the X, the Y and the Z. Now here I'm going to butcher the technicalities quite a bit, but we can kind of very roughly, and there is a lot of inaccuracy in what I'm about to say, but we can kind of, and it gives us a sense of why we need imaginary numbers. We can kind of go, well, we can associate each spin direction along a given axis with a number which is 1 unit away from the number 0. The reason we insist it's 1 unit away is due to essentially rules in quantum mechanics. So we can have the number 1 for the spin pointing along one axis, the number -1 for the spin pointing along a different axis. But what if the spin is pointing along the third axis? Well, we've run out of numbers. So in other words, we have to start inventing other numbers which have a size of 1, but which are not -1 or +1. In other words, they're numbers that don't exist on this real number line. And we call such numbers examples of imaginary numbers. Now, they're imaginary because no physical observable has a value equal to an imaginary quantity. However, they're vital for describing the universe, such as allowing there to be enough directions the spin can go in to describe an electron moving and being allowed to spin in 3D space. And because we live in a three-dimensional universe, at least in terms of the number of dimensions of space, that's very important. Now, it's worth saying that if you go into the technicalities, really represent spin using matrices, not numbers, but it still boils down to the idea that in the end, these matrices, called Pauli matrices, we can get two of them if we're considering 1 and -1, but to get the third Pauli matrix, which describes spin along our third axis, we need to start introducing imaginary numbers. So we mentioned that we need imaginary numbers to essentially have more numbers which have a size of 1. And this involves having numbers that don't lie on the real number line, and we call these numbers imaginary numbers. Well, we can think of placing imaginary numbers themselves on an imaginary number line. Now here language is a bit frustrating because I don't mean a number line that only exists in our imagination, although whether imaginary numbers only exist in our imagination is a matter I leave to philosophers. However, and it's a very interesting question whether imaginary numbers are in some physical sense real or not. Let us describe reality as we're exploring in this video. But the point is, we have a number line which is distinct from the real number line, and we call numbers on it imaginary, so we call the whole number line the imaginary numbers are on the imaginary number line. And because the imaginary number line is distinct from the real number line, we want to be able to plot a number and make sure that if we somehow connect these number lines together, the number is free to lie solely on the imaginary number line and have no component, if you like, on the real number line. That is, none of its parts are somehow real. Um, and therefore we can kind of think of a number which is imaginary as having all of its components along the imaginary number line and none of them along the real number line. And this is very analogous to how we would describe a vector. If we wanted to say a vertical vector, we would say, well, the vector lies along the y-axis, that is the vertical axis, and has no components along the x or the horizontal axis. Therefore, in analogy, we make the imaginary number line perpendicular to the real number line. We're just trying to allow us to talk about numbers which have no real components when we do this. However, we can clearly have 0 lots of an imaginary quantity, because an imaginary number is still a number, so we should still be able to think of 0 lots of imaginary numbers, and we should get 0. And therefore 0 is common to both real numbers and imaginary numbers. And is 0 real or imaginary? Well, because 0 represents the idea of nothing, it's as much imaginary as it is real. So we make sure that the imaginary number line also has the number 0 on it, just as the real number line does. So now we have two number lines which are perpendicular to each other, and they intersect at the number 0. Therefore, we have essentially now built up something that looks a lot like a graph in using x, y, or Cartesian coordinates. More mathematically, we could say, by considering the imaginary number line and the real number line, we have now constructed almost a plane, because we can think of any point now on this, on this graph. We can think of any point now as lying on a two-dimensional surface, where kind of the horizontal axis is our real number line and the vertical axis is our imaginary number line. So we have, in a sense, defined a plane by putting these number lines together, and we call this plane the complex plane, because it contains numbers which in general will be a mixture of real and imaginary, because if we have a point and the point doesn't lie along one of our axes, then that point represents a number that has a real component and an imaginary component. So we call that kind of number complex. So the complex plane is just a plane which contains all complex numbers. And we can think of imaginary numbers and real numbers as like very specific cases of complex numbers. And the diagram we have, so the plane along with our axes or number lines, is called the Argand diagram. It's just worth mentioning for those of you who might go on to use it, be it in engineering, physics, mathematics, you name it. And the beautiful thing is, looking at this diagram, we can immediately see when we have at least 4 numbers, which are 1 unit away from 0. For example, so like if I step to 1 step to the right, I get the number 1. If I step 1 step upwards from 0, I get the imaginary number plus I. If I step 1 step to the left from 0, I get minus 1, and if I step 1 step down from 0, I get minus I. So there's at least 4 numbers now with the size of 1. So we have definitely extended the numbers available to now account for enough dimensions of space to describe how an electron would spin, in all its possible degrees of freedom in 3D space. But we've actually done even better than that. And doing even better is important in things like quantum mechanics, where we actually need to do a lot better than just to have 4 numbers. We need an infinite number of numbers which have a size equal to 1. And we actually do have an infinite number of numbers, because if you think of a circle in this complex plane centered at the origin, so centered at the number 0, and the circle goes through, the number 1, the number I, the number -1, the number -I, so it's like, has, if you like, 1 unit radius, then any point, because we have this as a circle and all points on a circle are at the same distance from the centre as any other point, because for example number 1 lies on the circle and is 1 unit away from 0, all numbers on the circle are going to be 1 unit away from 0. And the circle we can think of as made up of an infinite number of points. So we are now actually in the complex plane have an infinite number of numbers which have a size equal to 1. And we call these unit complex numbers, and they're very important in quantum mechanics, and they're also very useful in classical physics. And we'll talk now a little bit about how kind of unit complex numbers and complex numbers generally are very useful for unifying 2 seemingly very distinct bits of classical physics. That is the growth of bacteria and also waves on a string, or similarly the motion of a pendulum. And then we'll be bringing the discussion back to quantum mechanics, and we'll talk about the points of imaginary numbers in Schrödinger's equation. And then at the end of this video, I'll talk about what's coming, hopefully coming later on in this channel. So, in our previous slide, we talked about building up the complex plane and developing the idea of a complex number. And that's very useful if we're thinking of a unifying phenomena in nature. Now, a lot of people think physics is things like solely stuff about electric circuits or maybe Newton's laws, and think physics is solely about inanimate objects, that it is somehow distinct from living objects and therefore biology. However, this isn't really true. Physics is about trying to find laws that unify nature and therefore bring together seemingly distinct phenomena and consolidate them into a single overarching idea. And maths tries to do a very similar thing. It tries to look at the language that is used to describe different phenomena and see if there is a common language that can describe lots of seemingly different phenomena at the same time. And complex numbers actually unify a lot of seemingly very different phenomena together, and in this sense are very powerful. So you might at first think, for example, that the motion of a mass when it's oscillating in a pendulum, like say, the motion of a metronome, if you like music, would be somehow distinct from the growth of bacteria in a petri dish. And there's definitely very good reason to think this, at least before one has seen complex numbers and used them a fair bit. And that's because If we think of how we would describe both of these processes using real numbers and therefore real functions, then they do seem to look very different. For example, if we think of the mass on a pendulum, and we say at time 0 it doesn't have any angular displacement from where it initially is, and then we want to plot its kind of displacement over time in terms of the angle at which it moves. Well, if this pendulum doesn't undergo wild oscillations, so it doesn't move very far from the equilibrium position, then the system is an example of what's called simple harmonic motion, and that's just a very fancy way of saying the object in the system is oscillating. And oscillations are generally described by sine functions or cosine functions. And for example, we have the red curve there, we have what the sine function looks like. And we can see the sine function is periodic. It repeats itself because as a pendulum oscillates, assuming it doesn't lose any energy, it's just going back and forth at the same amplitude forever until the end of time. So the sine function is periodic, and it also goes up and it goes down. However, if we look at the growth of bacteria in a Petri dish, well, one of the things that makes this seemingly very different from the sine function is that, for starters, we're talking about the growth of bacteria cells. So we have growth, i.e. not something that goes up and down. Not only this, but if you actually go through the maths, the growth of bacteria, providing there's enough sustenance where this growth isn't some way limited or diminished, because we don't have like bacteria running out of food or oxygen or anything, then we get an exponential curve. So not only does the curve increase, it increases at a faster and faster rate. And I wrote the function for the exponential curve here. When we're talking about exponential growth, we have something like e to the k of t, where k is a positive real number. We also have situations in nature of exponential decay, like if we have a radioactive source, because it's radioactive, the number of stable nuclei are diminishing over time, not increasing, and so we have exponential drop, exponential decay. However, for bacteria, as the number of cells is increasing, providing there's enough sustenance to sustain this, we have exponential growth. And comparing the curve for the sine function and the curve for exponential growth, we can see these two functions look very different. So it doesn't at first seem at all likely that there is at all a mathematical connection between them. We seem to be describing two completely different phenomena. However, we can unify both by thinking that both are specific cases of combinations of e to the I omega t and e to the minus I omega t. Now, e to the I omega t is a complex number, and if you want the proof of that, you use something called Taylor series, but for this video we're just taking on trust. E to the I omega t is a complex number, and as you might expect, it contains the imaginary number I, the square root of minus 1, our primary imaginary number from which we can build all other imaginary numbers out of. And the way that this actually unifies both functions of trigonometric and our exponential curve is that if we allow omega to take on different values, we can actually describe both using e to the I omega t, or combinations of e to the I omega t and e to the minus I omega t. So, for example, if omega is minus k times I, then you can use the definition of I, and I encourage you to do this if you're listening to this video and want a bit of an exercise. But you could show that if omega is equal to minus k times I, then e to the I omega t is, by definition, the exact same as e to the kt. In other words, e to the I omega t, this kind of function in the complex plane, can describe exponential growth, a real function, describing a very real process. Now, similarly, if we say omega is k, and we insist again that k is a positive real number, then using combinations of e to the I omega t and e to the minus I omega t, we can actually define or construct the sine function and also the cosine function. So the sine and cosine functions are really kind of combinations of e to the I omega t and e to the minus I omega t. So they're really combinations, if you like, of functions in the complex plane. Or we can think of it as a whole function in the complex plane that happens to just also reduce to a real function. So if we think about exponential growth and harmonic motion as kind of real functions, they seem to look different, but we can think of them as specific cases of a function in the complex plane, and in that way of thinking about it, actually these two functions are, in an abstract sense, kind of the same. And thus we can talk simultaneously about the growth of bacteria and the motion of your metronome as you're playing the piano. So that's part of the beauty of complex numbers. They allow us to unify it so much. And now, because this is a video on a channel mainly about modern physics, we're going to go back to our old friend quantum mechanics and talk about not just the use, but the vital importance of imaginary numbers in quantum mechanics, because as we'll see, without imaginary numbers, the start of quantum mechanics would have been crippled, which would have huge ramifications on our technological progress since really the early 1900s. So, as I've alluded to, imaginary numbers are very important in quantum mechanics, and actually their use goes back to the very early days of the subject, when we started exploring a topic called particle wave duality, where we saw particles behave like waves. But to get there, we really should start with waves we're much more intuitively familiar with, such as waves on a string. So we can see in this diagram, you can essentially kind of like periodically move your hand up and down, and you'll generate a wave on the string. And for those of you that are quite perceptive, you might realise this kind of shape looks a lot like the sine function we saw before. So generally, one can tell visually that we would expect a general equation that can describe such waves to allow real solutions. That is, to be able to describe the wave as a sine function or a cosine function or some mixture of sine and cosine functions. And those waves are fairly intuitive to us. And we used to think that this kind of physics was very separate from particles, you know, solid objects, you know, like laptops or microphones. And definitely laptops and microphones don't seem to display much of this oscillating behaviour, not naturally anyway. Something has gone very, very wrong if my laptop starts oscillating. It's not a normal thing for it to do, otherwise making YouTube videos would be very difficult. And we kind of presumes that this distinction was a very good distinction, even when applied to particles such as subatomic particles like electrons. However, we were wrong. That's a danger of relying on our assumptions too much. They're often, at least in the context of physics, our assumptions tend to be at fault if we based our assumptions solely on daily experience. So, for example, one thing you can do is you can send electrons, high energy electrons, through slits. Now, if you do this with light, which we know behaves like a wave, the light spreads out, it diffracts, and then different bits of the light, now the light is spread out, can kind of overlap with each other, and we say interfere, that is in some way interact, and that produces on the screen regions where you have very bright lines, where the two bits of the waves of light have kind of added together, and you also get much less bright regions where the waves have mostly kind of cancelled out. And it's this repeated pattern of bright lines and kind of darker lines which tells you that interference has occurred, and for that you would need the object that has passed through the double slits to have diffracted and interfered in a wave-like way. So it was presumed electrons couldn't do this. However, when we put electrons through double slits, they produced this interference pattern. So even though we've never actually seen an electron acting like a wave, this was one of the first, and as the decades went by, it became definitely one of the first. There became lots of pieces of evidence afterwards, but it was one of the first pieces of evidence that particles like electrons can actually behave like a wave. So the challenge was then to try to describe this mathematically, to come up with something very rigorous, very tightly constrained, such that we could then actually start using this idea practically. And a man called Erwin Schrödinger, took up the task. And what he was trying to do was have an equation that described the waveness, or if you like, the wave associated with the electron, which would be an analogy to the classical wave equation that describes waves on a piece of string. So the Schrödinger equation, which is what he came up with to talk about this, is essentially a wave equation but for particles like electrons. So sometimes these waves are called matter waves, and the Schrödinger equation is an equation that outputs a function which describes the shape of this matter wave. And naturally, one might think that he would be hoping for the function one gets out that describes matter waves to be a real function, or at least to be expressible as a real function, but alas no. All solutions to the Schrödinger equation, and we call these solutions wave functions, so all wave functions, by the very nature of the Schrödinger equation which he derived, turn out to have to be complex. That is, it is impossible to describe the wave nature of an electron or a matter wave solely using real numbers, because the wave function is inherently complex. There are no real solutions. Now, there are exceptions to this. You can put extra constraints on the Schrödinger equation and thus solve a slightly different equation called the Schrödinger time independence equation, and that does allow for real solutions. But the full Schrödinger equation that describes the full evolution of the wave does not allow for real solutions. So we kind of have to use imaginary numbers when talking about wave functions in quantum mechanics. And for those of you which are curious what the Schrödinger equation in its full time-dependent glory looks like, I have it here on the screen. It might not be obvious that the solutions to it are complex or have to be complex, but I thought it was worth sharing essentially anyway. And we could see that the Schrödinger equation does contain the imaginary number I, so it perhaps isn't, too confusing that, it would have to have kind of complex solutions, but I'm not going to go into the formal proof, though it's worth showing Schrödinger's equation here for completeness. Although if you are interested in mathematically where the Schrödinger equation comes from and one way to derive it, I have a video on that. Although there are many ways to actually derive Schrödinger's equation. So I'm going to finish this video by talking about ideas I have for what might be coming up in the future for this channel. So if you wanted to learn about imaginary numbers and why they're useful in physics, I will probably kind of stop here. But if you would also like to know what's coming up on this channel, particularly if you're new to the channel and wondering how it's going to progress, or if you've been here a while and want to see what's going to happen with it, I thought it'd be worth ending with a bit of that, and also gives us a bit of a break from mind-bending physics such as, matter waves. So for the future, there's lots of things I would really like to do for this channel in terms of the kind of content. Now, physics is huge. Physicists have a habit of hijacking almost any mathematics created by mathematicians sooner or later, so there is virtually no such thing really as pure maths, and so almost all areas of maths are also topics we could potentially cover in this channel, although I will try to stick to the science and physics. But even then, physics is very broad and can apply to everything in the universe, including, as we saw earlier in this video, in biology, when we talked about kind of the growth of bacteria cells, or growth of, number of bacteria cells. So, the scope of potentially this channel is quite huge. It's another reason it's good to talk about what might be coming up. So in terms of playlists, I'm hoping to continue the linear algebra playlist, so we'll probably move on that playlist. Now we talked a lot about matrices to talk more about vector operations, and hopefully have a video solely on just applying the maths to some physical system, and maybe something like acoustics, because we haven't really talked much about music or solid state physics on this channel, despite music being something I'm a massive fan of and is really core to the human experience in many ways. So hopefully some more videos on music and related to that, maths videos on linear algebra. I'll also go back to completing a playlist I began, but haven't continued with for a while. The playlist is really where I go through a book called Quantum Field Theory for the Gifted Amateur, and the brilliant thing with the book is it's kind of a book which is trying to help people learn quantum field theory, but doesn't presume that they're doing, a physics degree or something. The challenge with the book is it does assume a high degree of mathematical experience, but I tried to reduce it down and show the core ideas and make videos such that there's one video per chapter or something. So I'm hoping to go back to that. It's very time consuming to have to read the chapter and condense it down, but I think it's really worth doing because quantum field theory, very important in particle physics and has applications in solid state physics too. And I hope to make a new playlist on the life cycle of stars. I want to do a playlist because, properly broken down, the life cycle of a star is hugely complex, and I won't go anywhere near into all the complexities. However, trying to talk about all stages in one video would just make the video very rushed and probably quite unenjoyable. So I'll hopefully have one per, ebook, if you like, the star, or per part of its life cycle. Might have two on main sequence because our star is on the main sequence phase. So might have one generally on main sequence stars and one on the current properties of our wonderful sun. And then for off-topic or more like one-off videos, maybe more videos on music. So could talk about phonon physics, which is about how sound travels through solids. Could talk about standing waves, so how notes are formed on the string of a violin, or in the kind of air in the tube of a flute. And I'll also, hopefully, once I've done that, talk about how we can apply standing waves and therefore ideas that are built chiefly to explain music, to describe semi-classical models of the atom, like Bohr's model of the atom, and also how standing waves, or waves generally, can help us understand particular quantum systems fairly easily, like when we've got an electron very tightly trapped, so we say it's in an infinite potential well, or well approximated to be in an infinite potential well. I also hope to go through some academic papers for this channel and to really start covering more kind of hot news, if you like, in physics. So talk about kind of news headlines and stuff. And it's worth saying, if there's any topic you would like me to cover, or if there's any news article you would like me to go over, please comment it down below. I would love to hear what you would like me to cover, because this channel is about helping you and helping as many people as possible with exploring the wonderful properties of the universe, and therefore I would love to hear what you would like covered in this channel. And if something is mentioned where I feel I have the necessary expertise, because it's worth saying there's still huge amounts of physics I am woefully ignorant of, but if it's something I feel I can cover well, I'll do my best to make a video on it. So I hope you've enjoyed this video. I hope you've learned something about imaginary numbers, why they're important and why we keep talking about them despite nobody ever seeing them and them being in many ways imaginary. And I hope also if you got to this point in the video, you've seen some stuff coming up you might like. And as I say, any suggestions for what you would like me to cover, please comment down below. I hope you have a really good week. It's really warm, at least kind of if you're living in England, so please enjoy the sun, and if you're not living in England and it's sunny, enjoy the sun. And if it's not sunny where you are, or you happen to be listening to this on a very rainy day, then enjoy the most of the weather and the outside, whatever that might be, and don't spend too long watching YouTube videos either. Well, I hope you have a really good week, and hopefully see you for more physics and applications of maths to physics fairly soon.